Welcome to the university. We offer lectures related to science and mathematics. We also at times create content related to other learning areas. If you like this channel, please extend your support by giving us a like, share our contents, and subscribe to the university, and don't forget to click the notification bell to get updated whenever we post new videos. Our topic in this video is about electromagnetism. We will start our journey as we trace the origin of one of the four fundamental forces in nature, the electromagnetic force. The Big Bang Theory explains the origin of the universe. It claims that all history of the universe dates back at the Planck's time, which is 10 to the negative 43 seconds. The temperature during this time is astronomical and believed to be around 10 raised to the 31 degrees Celsius. During this state, all matter were in a soup-like form made from the fundamental particles of nature. It is because of the amount of thermal energy that the singularity poses. This is due to the fact that thermal energy affects phases of matter. They said to be compressed in a space like the size of a proton. It is believed that soon after 10 raised to the negative 43 seconds, gravity separates itself and became the first fundamental force of nature. From 10 raised to the negative 43 seconds to 10 raised to the negative 35 seconds, the three remaining forces, namely, the strong, weak force, and the force of electromagnetism, were united. At around 10 raised to the negative 34 seconds to 10 raised to the negative 32 seconds, the strong force separated from the electroweak force, which is still conjoined with the electromagnetic force. There is also an astronomical inflation. Imagine a tennis ball that grows to that of the size of the solar system in just a matter of small fraction of time. Time passed by, the amount of thermal energy decreased. This happens at t is equal to 10 raised to the negative 12 seconds, and the temperature around this time is 10 raised to the 15 degrees Celsius. The universe takes shape around 10 to the negative 6 seconds. After inflation, 1/1,000,000th of a second after the Big Bang, the universe continues to expand, but not nearly so quickly. As it expands, it becomes less dense and cools. The most basic forces in nature becomes distinct. First is gravity, then the strong force, which holds the nuclei of atoms together, followed by the weak and electromagnetic forces. Billions of years have passed, and mankind started exploring the fundamental forces one by one. We will explore the electric force. This is the type of force that acts between charged particles. It can be repulsive or attractive depending on the nature of interacting charges. The law of charges states that like charges repel and unlike charges attract. This force is calculated using the formula F sub E is equal to the products of constant K times the magnitude of charge sub 1 and magnitude of charge sub 2, divided by R, raised to the power of 2. This formula or law tells us that the larger the magnitude of the interacting charges, the stronger the force will be. The smaller is the distance of separation, the stronger will be the force. The magnitude of the electrical force is directly proportional to the magnitude of the charges and inversely proportional to the square of the distance that separates them.
Hello guys, welcome back to the university. In this video, we're going to teach you how to solve the electrostatic force that exists between charges. So let's go and let's have a sample problem. And we are going to solve this sample problem completely. The sample problem tells us to calculate the electrical force that exists between two protons, which are placed 1.5 times 10 to the negative 9 meters apart. We are also given a data right here about the electric constant K, and it has a value of 8.99 times 10 to the 9 Newton times meter squared all over coulombs squared. Alright, so let's have step 1. So what will be our step 1? So I think it is much easier for you guys if you were able to have a picture of the problem inside your mind. Alright, so you need to draw the situation, because if you can do that, I think you can attack the problem with ease. So I'm using this diagram that shows us two protons which are separated by a certain distance apart, and you will see that the lines of force are diverging. This means that they tend to push one another apart, and you will see that we have a repulsive force that exists in between them. Alright, so I hope that you were able to grasp the illustration and what is being asked by the problem. So it is asking you if you can find the force, the amount of the repulsive force. Alright, so step 2 is know your data. Okay, some data are not included in your problem or not stated, but your teacher knows that you have prior knowledge about the subject matter, and you can use those prior knowledge in order to get all the data that you need in order to solve the problem. In our case, I have already included it. So we have the value for the charge of the proton, which is 1.6 times 10 to the negative 19 coulombs, and we also have the distance of separation, which is 1.5 times 10 to the negative 9 meters. And we also have the value for K, which is 8.99 times 10 to the positive 9 Newton times meter squared per coulomb squared. So that's our step 2. Next is step 3. So for step 3, identify the equation or equations that you have to use. Basically, it can be one or two or more equations. It depends on the number of variables that you are looking. Okay, so for our problem, this is the formula for the electric force or the electrostatic force. So Fe is equivalent to K, okay, which is the electric constant, multiplied by the value of the magnitude of the first charge times the value of the magnitude of the second charge, divided by the distance, or the square of the distance of their separation. So you now have the formula. I think by the data we can already substitute, but wait, so there's more. So you can actually do step 4 first, and you can also check if there is a hidden problem. Sometimes students jump readily to the substitution of the data to the variables or to the equation, but they did not check if there are hidden problems, so the resulting answer is wrong. Alright, so because it is better if we check. So if there is no hidden question in the problem, you can now substitute your values to the equation. Okay, so step 5, we have step 5. Alright, so step 5 is to substitute the values. So to this equation, so F sub E, okay, is equivalent to K times Q sub 1 times Q sub 2 all over R squared. And upon substituting, you will see that the values are, your equation will look like this. Alright, so you have 8.99 times 10 to the 9. Alright, so this thing right here is actually the units. So I put the units because later on we're going to do the dimensional analysis to show that the units are correct. So it's upon plugging in, and you can actually press it in your calculator, you'll find out that it is 102.28 times 10 to the negative 12 coulombs or newtons. Okay, so it does not have any unit right here, but the unit here is newtons, and here we're gonna show why it's newton. So step 6 is to affix the correct unit, or we are gonna use the dimensional analysis. Alright, so from this equation, so we have the unit for K right here, so that's Newton times meter squared. Okay, divided by coulomb squared. So the unit of charge is C, or coulomb, so C times C is C squared. And the value for, or the unit for the distance is m, and then you have to raise it to the power of 2. Okay, so you will see that all right, okay, I'm gonna use my pen right here, that this will cancel out. Okay, yep, so because this one is just c squared and it's in the numerator, so this thing will cancel out, and also this one, because m times m is m squared, and it will cancel out. So the unit for that is Newton, so you're gonna use n for newtons. Okay, so I hope you guys learn how to properly solve the electrostatic force that exists between charges.
The electric field. How do charges know where the other charges are located? The electric force is distributed over an area. It shares the properties of electric force acting over it, making it an electric field. Strength of the electric field. This is the amount of electric force acting over a charge. The formula for the electric field E is equal to F sub E, the electric force, divided by the magnitude of the charge, Q. This depends on the absolute magnitude of the charge and the distance at which the test charge is placed. Work done by an electric field. The electric field can move or affect charges in its vicinity. Hence, the electric field can do work on charges. Work is defined as the product of force and displacement. We also know that the formula for the electric field E is F sub E over charge Q. We can simplify this, and we will see that it is equal to K times Q over R squared. And therefore we see that the electric force, F sub E, is equal to electric field E times charge Q. So the amount of work done by the electric field on the charge is computed by substituting this expression for F. We find that work W is equal to the product of charge Q times the electric field E times the displacement. We now define voltage. Voltage is the amount of work done per unit charge. We have voltage V is equal to work W over charge Q. We have a formula for the work done, and this is equal to the electric force F multiplied by the displacement D divided by the charge Q. We also know that F sub E is equal to the electric field E times charge Q. When substituted to the formula, we find that voltage V is equal to the product of electric field E and the displacement D. We can try to formulate an equation to count charges. We should recall that particles have charges that is either positive or negative. Electrons have negative charge. It has a magnitude of negative 1.6 times 10 raised to the negative 19 coulombs. The mass of the electron is 9.1 times 10 raised to the negative 31 kilogram. The proton has a positive charge, and it has a magnitude of 1.6 times 10 raised to the negative 19 coulombs. The mass of the proton is 1.6 times 10 raised to the negative 27 kilogram. The total number of charges is an integral multiples of the basic magnitude of charge times n. We have a formula for Q, which is equal to n times E. Electric current. Streams of electrons that are moving. Electrons are more mobile compared to protons. Electric current is defined as the number of charges that passes through a given point per unit time. We have current I is equal to Q over T. The unit is ampere in the honor of a scientist named André-Marie Ampere. It is also equivalent to charges that pass through a given point per second. 1 ampere is equal to 1 coulomb per second. We can now discuss the movement of the electrons. Electrons move in random direction. The resulting electric field ensures that there is a net displacement. As we can see in this diagram, the length of this conductor is delta x, which is equal to the drift velocity of the electron and the change in time delta t. The total number of electrons in this conductor is related to its concentration per unit volume. Volume of this conductor is V, is equal to area A, times the drift velocity, times delta T. We can see that the total number of electrons inside the conductor at any given time is equal to Q, which is equal to N times V. This is equal to N times Q times A, multiplied by the drift velocity, and delta T. We see that if the number of charges changes per unit change in time, the current in the conductor is given by I, is equal to delta Q over delta T. This is equal to N times Q times A times the drift velocity V sub D. We can try to find the electric current per cross-sectional area. The current per cross-sectional area is called current density J. It has a formula, current density J is equal to μ over A. We will see that current density J is equal to N times Q times the drift velocity V sub D. The units for the current density J is equal to amperes per square meter. We can also explore the relationship of current density J to resistivity. We find that current density J largely depends on the magnitude of the electric field. Different materials reacts differently to electric field. In metals, the current density J is directly proportional to E. This relationship is called the Ohm's law. Discovered by the German physicist George Simon Ohm, 1787 to 1854, in 1826. We define the resistivity ρ of a material as the ratio of the magnitudes of electric field and current density. We have a formula for the resistivity ρ is equal to E over J. The electric field E is found using the equation ρ times current density J. We know that energy is lost during collisions. If we have a conductor with uniform cross-sectional area and uniform length L, and we apply an electric field, charges will react to the field and a potential difference will develop at the ends of the conductor. Charges tends to flow from higher voltage region to lower voltage region. The energy possessed by the charges is gradually lost because of numerous collisions. From the previous definition of current and voltage, we can see that voltage V is equal to E times L, where L is the length of the conductor and current I is equal to current density J times A. Solving for E and J gives us E is equal to V over L, and J is equal to I over A. We can substitute this to the equation of resistivity and find the amount of resistance in a circuit. We can see that the resistivity ρ is equal to V times A over I times L. We cross-multiply L and A to the resistivity and find out that ρ times the ratio of length L over area A is equal to V over I, which is equal to the resistance R. This is also the formula for the Ohm's law. R symbolizes the resistance in the circuit. Resistivity ρ has unique values for each material. We see that the resistance increases as there is also an increase in the length of the conductor. We shall also see that the resistance decreases if the cross-sectional area of the conductor is also increased. The formula for the Ohm's law is resistance R is equal to V over I. We can now try to compute for the power in the circuit. Power is defined as the rate energy is delivered or converted per unit time. This is also defined as the amount of work done per unit time. The formula for power is P is equal to energy E over delta T, which is also equal to work W over delta T. The unit of power is called watt, in the honor James Watt. We can use the definition of voltage to find the amount of work done per unit charge. We see that the change in work denoted by delta W is equal to delta V times the charge Q. Substituting this to the equation of power, we find out that power P is equal to delta V times delta Q over delta T. This is equal to power P is equal to V times I, or P is equal to I squared R. We now discuss the twin of electricity, which is known as magnetism. Intuitively, you may think that electric force and magnetic force are one of the same thing. Let us start our journey in this topic as we explore the origin of magnetism. It can be proven that a moving charge creates a magnetic field. According to kinetic molecular theory, atoms vibrate in response to thermal energy. Therefore, we can say that all of us generates a magnetic field since our temperature is above the absolute temperature where all vibrations have ceased. Magnetic moment arises when a charge travels in a closed area. We can say that even the hydrogen atom has a magnetic moment, because the hydrogen atom has one electron that revolves around the nucleus. Therefore, we can say that the movement of the electron in a closed loop creates a magnetic moment. The magnetic moment generated by the electron is given by the formula mu is equal to I times A. A is said to be the area of the orbit. I is equal to the current. We can now rewrite the equation above as mu is equal to Q over T multiplied by A. We all know that the electron is moving with a certain velocity, v. The electron completes its revolution in a specific time frame known to be the period. We use the variable t to denote the period of motion. Knowing the velocity v of the electron is equal to the distance traveled by the electron, which is equal to the orbit or to the circumference of the hydrogen atom, which is equal to 2 pi r divided by the time or the period t. We can solve for the period t and find out that this is equal to 2 pi r over v. The frequency is the inverse of period t. This is equal to 1 over t, which is equal to v over 2 pi r. Therefore, it goes to show that the magnetic moment, mu, is equal to I, A equal to Q over T times A is equal to E times V over 2 pi r times pi r squared. We now simplify the equation and find out that the magnetic moment mu is just equal to E times V times r over 2. The magnetic moment is related to the angular momentum of the electron. The angular momentum of the electron is denoted by L. This is equal to the mass of the electron multiplied by the velocity and the radius of the hydrogen atom. We can solve for r. We can see that r is equal to L over m times v. We can substitute this to our formula for the magnetic moment mu, which is equal to E times v times r over 2. Since we know that r is equal to L over mv, we plug it in. The resulting equation is mu is equal to E times the angular momentum L over 2 times m. In quantum mechanics, the angular momentum is a fundamental quantity and it has an equivalent formula equal to h over 2 pi, where h is the Planck's constant. We substitute the formula for L in our previous equation and find out that the magnetic moment of the hydrogen atom, also called as Bohr magneton, read as mu sub b, is equal to E times h over 4 pi times m. The electron also has its intrinsic property, called as spin. This is analogous to the way how the Earth rotates on its axis. This is also related to a magnetic moment, which is almost equal to that of 1 Bohr magneton, 1.001 Bohr magneton. The uniqueness of the magnetic moment per atom is the reason why some materials are easily magnetized while some are not. We now formally introduce the types of magnetism. As mentioned earlier, magnetic behavior depends on the orientation and distribution of electrons in the atom. The first classification of material according to their magnetic property is known as paramagnetism. In most materials, their magnetic moment is up to 0. However, in some cases the atom has a magnetic moment that is in the order of the Bohr magneton. When such a material is placed in the presence of an external magnetic field B, the field exerts a torque on each magnetic moment, causing the magnetic moments to align. The additional magnetic field contributed by the material is proportional to the magnetic moment caused by the electron. The total magnetic moment of the material per unit volume is called as the vector quantity known as magnetization of the material, denoted by m, which is equal to the total magnetic moment divided by the volume V of the material. We can compute for the additional magnetic field of the material. This is denoted by B sub p, which is equal to mu sub 0 multiplied by the magnetization of the material, m. If such a material surrounds the current-carrying conductor, the total magnetic field produced by this interaction is given by magnetic field B is equal to the original magnetic field B plus mu sub 0. Such a material is called a paramagnetic material. The magnetic field of the material is enhanced by a dimensionless factor K sub m. This is known as relative permeability. The value of the relative permeability is different for different materials. For common paramagnetic solids and liquids at room temperature, typically ranges from 1.00001 to 1.003. The magnetic permeability, denoted by mu, is given by the formula mu is equal to K sub m times mu sub 0. Magnetic susceptibility of a material is the difference between the magnetic permeability and unity. This is given by the formula X sub m is equal to K sub m minus 1. This is also a dimensionless quantity. The tendency of magnetic moments is to align themselves parallel to the magnetic field where the potential energy is minimum. However, we know that thermal energy, heat, tends to randomize the motion of particles, electrons, and of course of atoms. For this reason, magnetic susceptibility tends to decrease with increasing temperature. The law relating temperature to magnetism is called Curie's law. It is described as follows: the magnetization M is inversely proportional to the absolute temperature. This can be expressed using the formula M is equal to C times B over T. This relationship is called Curie's law, after its discoverer, Pierre Curie, 1859 to 1906. The quantity C is a constant, different for different materials, called the Curie constant. The second type of magnetism is called diamagnetism. Some materials have magnetic effects because an external field alters electron motions within the atoms, causing additional current loops and induced magnetic dipoles comparable to the induced electric dipoles. In this case, the additional field caused by these current loops is always opposite in direction to that of the external field. An induced current always tends to cancel the field change that caused it. Such materials are said to be diamagnetic. They always have negative susceptibility and relative permeability slightly less than unity, typically of the order of 0.99990 to 0.99999 for solids and liquids. Diamagnetic susceptibilities are very nearly temperature independent. The third type of magnetism is called ferromagnetism. Ferromagnetic materials that includes iron, nickel, cobalt, and many alloys containing these elements. In these materials, strong interactions between atomic magnetic moments cause them to line up parallel to each other in regions called magnetic domains, even when no external field is present. The total magnetic moment of a domain may be many thousands of Bohr magnetons. The torques that tend to align the domains with an external field are much stronger than occur with paramagnetic materials. The relative permeability is much larger than unity, typically of the order of 1,000 to 100,000. As a result, an object made of a ferromagnetic material such as iron is strongly magnetized by the field from a permanent magnet and is attracted to the magnet. It is quite obvious that a magnetic field present has an effect to moving charge. If we have a moving charge or a stream of moving charges, we therefore have a current. The net effect of an external magnetic field B on a charge depends on four factors. Magnitude of the charge, strength of the external magnetic field B, particle's velocity. The force is perpendicular to both B and V. If the charge is at rest, it experiences zero force. The force resulting from the interaction of the moving charges to the present magnetic field is given by F is equal to Q times velocity V times the magnitude of the present magnetic field. The formula given above is not deduced theoretically but was formulated through experiments. It is a product of our observation to the said phenomena. We use the right-hand rule to tell the direction of the force in the charged particle. The right-hand rule states that, to determine the direction of the magnetic force on a positive moving charge, point your right thumb in the direction of the velocity, v, your index finger in the direction of the magnetic field, b, and your middle finger will point in the direction of the resulting magnetic force. We now introduce the units of magnetic field. The unit used to quantify magnetic field is called Tesla, in the honor of Nikola Tesla, 1856 to 1943. The unit must be the same as the units of F over Q, V, therefore, the SI unit for B is 1 Newton times seconds over coulombs times meters. But since define the ampere as 1 coulombs per second, we can write 1 Tesla is equal to 1 Newton per ampere times meter. Another units used is called as Gauss. This is in the honor of the eminent mathematician and physicist, Carl Friedrich Gauss, 1777 to 1855. 1 G is equal to 10 to the negative 4 Tesla. We can visualize the presence of magnetic field by drawing magnetic field lines. We can represent any magnetic field by magnetic field lines, just as we did for the Earth's magnetic field. The idea is the same as for the electric field lines. We draw the line so that the line through any point is tangent to the magnetic field vector at that point. Just as with electric field lines, we draw only a few representative lines, otherwise, the lines would fill up all of space. Where adjacent field lines are close together, the field magnitude is large.
Welcome to the university, and in this video we are going to answer the question, how strong is the electric force compared to the gravitational force. But before we do this, please extend your appreciation and give us a like, share our contents, and don't forget to subscribe to the university, and don't forget to hit the notification bell to get updated whenever we post videos like this. So let us start our journey by making a comparison between the magnitude of the force of gravity and the electric force. So I have here a formula which is Fe all over Fg, and we know that Fe is the electric force and Fg is the force of gravity, and it has an equivalent formulation of Fe for the numerator all over our denominator, which is Fg, and it has an equivalent form of for Fe we have K times the magnitude of Q sub 1 times Q sub 2, wherein Q sub 1 is the magnitude of the charge of the proton because that's positive, and we have the magnitude for the charge of the electron because that's negative. And here R is the distance of separation between the two charges, and K is just a constant. And later on, I'm gonna reveal the value of K. So for the force of gravity, we have G here, which is the universal gravitational constant calculated by Henry Cavendish. And since it involves gravity, we need the mass of the proton and we need the mass of the electron, and we have to multiply them and divide them by the distance of separation, r squared. Alright, so let us simplify this formula by multiplying the numerator. So this part should be multiplied to the denominator and create the new numerator, which is K times Q sub 1 times Q sub 2 times r squared, and the denominator of the numerator times the numerator of the denominator. So that would create the new denominator, G times m sub 1 times m sub 2 times r squared. Alright, so I hope you follow that, and then you will see that r squared will cancel out because they are the same term or similar term, and r squared divided by r squared is just equal to 1. Alright, so let's proceed and substitute the value. But first, let us see the simplified equation. Fe all over Fg will look like this. Yeah. Yep. So, and then from here on, we are going to substitute. Alright, so K has a value of 8.99 times 10 to the 9 Newton times square meter all over coulomb squared. So the value of the charge is 1.6 times 10 to the negative 19 for the proton. It's also the same value as that of the electron to make the atom electrically neutral. Alright, so that's equivalent to saying 1.6 times 10 to the negative 19 C to the power of 2. So C to the power of 2 all over C to the power of 2 will cancel out. Alright, so what will remain here in the numerator as a unit is Newton times square meter. Alright, so what we're gonna do right now is multiply 8.99 times 10 to the 9 times 1.6 times 10 to the 19 raised to the power of 2. Alright, so you just have to make sure that you execute the exponent first before the multiplication. Alright, so here in the denominator, value of G is 6.67 times 10 to the negative 11 Newton meter squared. Alright, all over kilogram squared or squared kilogram. Okay, so right now we have the mass of the proton, which is 1.67 times 10 to the negative 27 kilogram times 9.1 times 10 raised to the 31 kilogram. So kilogram times kilogram is kilogram squared. So you will see that the term will cancel out, and what remain here in the denominator is Newton times square meter or meter squared, and this will also cancelled out. So since there's no unit, this is just a pure number. Alright, so next step is to press this in your calculator, and you will see that the answer is Fe is 2270 times 10 to the 36 times stronger than the force of gravity. So it's much stronger compared to the force of gravity by a factor of 10 to the 36 times. Alright, or 10 to the 39 times if you round up to 0.270 times 10 to the 39. Alright, so this is the answer. It is 2270.47 times 10 raised to the 36 times stronger than the force of gravity. So thank you guys for watching the university. I hope watching this video and staying with the university. So please don't forget to click the subscribe button, hit the notification bell, give us a like and share our content so that others will learn about our channel. Alright, so bye bye. Hope to see you soon again in the university.
Welcome to the university. In this video we're going to discuss how a charged particle behaves under the presence of an external magnetic field. But before anything else, please extend your appreciation, give this video a thumbs up, share our contents, and please subscribe to the university and hit the notification bell to get updated whenever we post new videos like this. Effects of magnetic field in moving charges. We can use the right-hand rule to show and determine the orientation of the magnetic field and force with respect to the velocity of the particle when moving in an external magnetic field. We will see it in the animation. That when a charged particle passes through an external magnetic field, it changes its trajectory as a result of the interaction of the external magnetic field and velocity of the particle. We will see that it is a curved path just like a circle. We can equate this to the formula for circular acceleration and be able to find information about the charge. Remember that the force felt by the particle is equivalent to the magnetic field B times the charge Q and times the velocity of the charged particle V. The formula is F is equal to B times Q times V. We also know that the force is equivalent to the mass of the object times acceleration. We can equate the two equations, that is, ma is equal to b times q times v. Remember that circular acceleration has a formula of v squared all over r. We substitute this for the acceleration and we will come up with the formula mass times the quantity of v squared all over r is equal to b times q times v. We can simplify this equation by dividing both sides by v and it will be equal to the mass of the object m times the quantity of v all over r, which is equal to b multiplied by q. Then we can solve for r, and we will find out that this is equal to the mass of the object, multiplied by velocity of the charged particle divided by the magnetic field B multiplied by charge. Since mv is equivalent to the momentum p, we can rewrite this equation as r is then equal to p divided by the product of magnetic field B and charge q. This periodic motion will repeat over and over again. Hence, we can get the formula for the frequency of this charged particle when moving in the presence of an external magnetic field. We know the formula for frequency f is equal to v all over r. And solving for the frequency will give us f is equal to b times q all over m. This is the formula for finding the cyclotron frequency in particle accelerators.